to our first Present Your Thesis series. We hope that during this period of severe and unforeseen circumstances, you and your families are remaining safe and well. Oops, sorry. The speaker will present for 25 minutes and then take questions from the audience. You can express queries and thoughts through the chat box section. So please reduce the greetings in this section and use it just for the questions. EFSTATHIOS, ADAMOPOULOS, and MARGARITA SKAMANTZARI will be moderating the Q&As at the end. We want to inform you that no offensive language, spamming, or mansplaining will be tolerated. Mute your microphone to help keep background noise to a minimum. Switch off video to improve network bandwidth. Only the speaker should have on his or her video. So, today's talk will be with Arnadi Murtiyoso, who will present his thesis entitled Geospatial Recording and Point Cloud Classification for Heritage Buildings. Arnadi Murtiyoso holds a bachelor's degree in geodesy and geomatics from Bandung Institute of Technology and an engineer's diploma in topography from the National Institute for Applied Sciences, Strasbourg, and is currently pursuing his PhD degree in photogrammetry and geomatics from the University of Strasbourg. His current research that he's going to discuss in a while involves photogrammetric bundle adjustment, point cloud segmentation and classification, and automation in 3D modeling for heritage objects and sites. So Arnadi, we're very happy to welcome you today, and please, you can start by sharing your screen, and the platform is all yours.
Thank you, Joe, for the introduction. So let me just try to share my screen here. So can you see my slides?
Not yet, but it's working, I guess.
It takes some time, yeah?
Yes, it worked. So
okay.
Go ahead whenever you think you're ready.
Okay, so thank you again for the introduction, and hello everyone, ladies and gentlemen. Today I would like to present a shortened version of my thesis in 25 minutes. So my thesis is entitled Geospatial Recording and Point Cloud Classification of Heritage Buildings. I'm doing this PhD course in the University of Strasbourg, in INSA Strasbourg, under the supervision of Pierre Krusenmeyer. So let's start. This is the outline of my presentation. First, I will introduce to you some backgrounds to the research. So the thesis itself is divided into two parts. The first part is called the geospatial recording of heritage, and the second part concerns the point cloud processing. So as an introduction, this is something that, of course, we have seen quite some time within CIPA and also in the CIPA emerging professional circles of the background of why we should record heritage buildings. I guess that the main reason is that it is very important to preserve our legacy, and with the technologies that we have today, we can do so virtually. And we know today that there are a lot of threats that can affect cultural heritage, both natural. Here, for example, we have the 2015 Nepal earthquake, but also anthropological, like the case with the Notre Dame de Paris in 2019. So in order to perform this recording, I present here a workflow for the 3D recording process. So we usually start with the input data, which is usually it consists of geospatial data. And in the case of 3D recording, it mostly consists of data acquired either from photogrammetry or laser scanning. And of course, there is a very important part of quality control that we have to take into account. And the point clouds that we create from photogrammetry and laser scanning, we can then use in the 3D modeling part. And here we also have the automation part, which is also very interesting research subject. And of course, to top it all, we all hope to be able to create an HBIM at the end of all this process. So HBIM is the Heritage Building Information Model, and it's a very useful platform in the management and management of the heritage point cloud data. So in this thesis, as I said previously, there are two parts. The first part concerns the, let's say, the acquisition part, the geospatial recording and quality control. And the second part consists the processing, the point cloud processing algorithms that I developed during this PhD thesis. So here I present to you some of the research questions that I asked myself during the research. First of all, for the first part, for the geospatial recording and quality control, the first question is naturally how we can thoroughly record a heritage site, because sometimes a heritage site is not only a single monolithic building, but consists of a set of other objects also. So for this, I propose a solution in the form of multi-sensor and multi-scalar approach, which of course I will explain a little bit in detail later on. The second question for the first part is the question of quality control. How can we control the quality of this data? And in this thesis, I tried to use some open source solutions in order to do this, to do the quality control. And then we come to the second part, the point cloud processing algorithms. And here we have the first research question: how to manage the point cloud data now that we have acquired them and controlled their quality. What I developed during the thesis is a progressive multi-scalar classification. And the second question is, can we automate some parts of the 3D model, 3D processing chain? And in this case, I propose a toolbox, which I will also explain later, which involves the functions made with the algorithmic approach. So we enter now to the first part of the thesis, the geospatial recording for heritage. And in essence, this part wants to answer the question of how can we generate point clouds for heritage building, but also how can we guarantee their geometric quality. So the main background of this part of the thesis is that nowadays we see a large diversity of 3D sensors. We have terrestrial laser scanners, we have drones, we have handheld laser scanners, we have photogrammetry, and of course we have also the classical traditional surveying methods to record heritage. And what we have seen these days is a move towards data integration rather than confrontation of these heterogeneous sensors in order to integrate them in the same system. And all of this is nice and good, but the problem is, of course, this also increases the complexity of the point cloud with which we will have to work on. So this is the approach that we propose in this thesis, is to divide the object into several, what I call here the scale steps. So here, for example, in this particular example, we have the scale step 1, which involves the historical complex and its surroundings. Sometimes it's useful to get an idea, a general idea, a bird's eye view of the historical complex for geographical, historical, socio-historical context, and so on. And here we use, for example, a drone. And then for the next scale steps, the scale step 2, we concern ourselves with the building complexes itself. And here we can use a drone and a terrestrial laser scanner. And then we enter into the third scale step in which we work with the individual buildings. And finally, we work with the architectural elements which are in those buildings. And here we can, for example, make use of terrestrial photogrammetry. Next, the question of quality control and why is it important. So this is a case study. Here, for example, I have Metashape. I am sure that it is one of the most used software, photogrammetry software in the market today. Some of you may know it as PhotoScan previously. It was developed by the company Agisoft. And it's quite flexible, as it can be used for both aerial and terrestrial images. And what is also nice is that we can perform automation using Python scripts and so on. And here I have a very crude workflow of photogrammetry within Metashape. So we start with the line image, we input the ground measurement, and then we can create the dense point cloud and so on. But even if we concern ourselves only with the first two steps, already there are a lot of questions that we can ask regarding the quality of the results of the software. For example, what kind of bundle adjustment is used in this part? What is the quality of the self-calibration? What about the precision of the exterior orientation parameters? Are the 3D markers in Metashape used as weights in the bundle adjustments? These questions are things that understandably commercial softwares would not divulge to their users. But this this gave rise to the next questions, in that how are we able to say that the results from Metashape is good? And in that case, how can we detect the errors in our project if we can verify that the result is not good, for example? And if we can detect those errors, can we increase the quality of our projects by eliminating those errors? So we enter now the toolbox that we also developed for this purpose, which is called the Damped Bundle Adjustment Toolbox, or DBAT, which was originally which was originally developed to test some damping techniques in bundle adjustments. But one of the main advantages of DBAT is actually that it provides comprehensive statistics, like a posterior variance and the correlations between the estimated parameters and tie points and so on. And this is very useful in assessing the quality of photogrammetric project. So here we have some examples of the use of DBAT in the case of close range UAV or drone projects, camera calibration, large format aerial images, and so on. And it is written in MATLAB, but the source code is open source. This means that everybody can download it and play around and test, do experiments with it. So I will show you just two data sets as to illustrate how DBAT can be used as a photogrammetric quality control. So these are some of the statistics that we can generate using DBAT. And here we can, in the case of these two data sets, for example, we see that we can use it to detect some problematic parts of the project. Here, for example, we see a spike in the spatial standard deviations for the for this part of the project. Also here, in this case, for the rotational standard deviations, and in the second data set, we also see a spike in the rotational standard deviations for these images. So, of course, in this case, we can then say that these parts of the project may be improved in order to increase the quality of the project. Another subject that is also interesting to address is the integration of the data. So we have the photogrammetric and terrestrial laser scanning point cloud, and then how should we do it if we want to integrate those two point clouds? So here it's a case study that I have here. That here I have the exterior of a church, which was recorded using UAV photogrammetry, and the interior was scanned using a terrestrial laser scanning. But the problem is that the two data sets were taken in different times. So the UAV in 2016 and the laser scanner in 2017. This means that there wasn't a lot of overlap between the two data sets. So we tested two methods to integrate the two point clouds. The first one is what I call the independent georeferencing method. In this case, the photogrammetric project was georeferenced using absolute orientation, and the laser scanning was also georeferenced independently from the photogrammetric project. And then because the control points are in the same coordinate system, they were automatically integrated at the end of the georeferencing process. The second one, the free network method. In this case, what I did was that I performed a registration first, or a relative registration between the photogrammetric and the laser scanning one. And then from the registered point cloud, the georeferencing was performed in order to take it into the coordinate system that we want. So here we see for the independent part is quite easy to use because of course you only need to georeference it the data sets directly, but we see some systematic errors here, for example, in the front of the church, while with the free network one, we observe that the error is more evenly distributed, which is thanks to the block adjustment during the registration and georeferencing. But of course, the problem is that for the free network to work, we need tie points between the two point clouds. And those tie points were observed manually. So we asked the question if automation is possible in this regard. And this is just a little experiment that I did. And the short answer is that yes, it is possible. But of course, unfortunately, this is not the main objective of my thesis. So this is only to show you that, an automation process is possible, and in most times it is required in order to reduce the resource time and resources needed. So to close this first part of the thesis, some thoughts and open questions. Of course, the multiscalar approach enables us to perform a thorough recording. And DBAT was the open source toolbox that we use as a quality control tool. And what is interesting is also that metric assessment is becoming more and more apparent, even in commercial software. I guess they understand the demand from users that metric assessment is important in some projects. And we have seen this case with Metashape, for example. And that data integration depends strongly on project requirements, but in any case, automation is always useful. And of course, since this is the world of research, you answer some questions and you get a lot of other questions that you don't have the answers to. And some of the questions that rise new from these experiments are, for example, which metrics are actually useful in DBAT, because there are a lot of metrics which some of them might not be very useful for quality control. Can we predict the metrics before the mission is performed, which would be very useful for the user? Also, how are we supposed to classify the very large data that we get from this multi-scale and multi-sensor documentation? And is there other alternatives for data integration? And now we enter into the second part of the point cloud processing part of the thesis. And in essence, here we want to answer the question of, okay, now we have the point cloud, we can guarantee that the point cloud is of good, high quality. Then what do we do with it? Because a point cloud, in any case, a point cloud is still just points. You don't have any tangible information with these points. So we have to do something with it, and we want to try to answer this in this part of the thesis. These are just a quick overview of several approaches in point cloud processing. We have some studies doing region growing. Others use model fitting, for example, RANSAC and MLSAC to fit the point cloud into mathematical models. There are other studies that also use geometric rules. For example, here we can determine the different floors of a building based on the altitude of the point cloud. And of course, nowadays we must also talk about machine learning and its subset deep learning for point cloud processing. So this is a toolbox that I developed during this PhD thesis. I call it M-Heracles, which stands for Heritage by Point Cloud Processing from MATLAB. And in essence, it concerns this part of the thesis. And here, the toolbox is meant to perform segmentation and classification in the special case of heritage point clouds. And how it does it is that it performs progressive multi-scale classification from the scale of heritage complex point cloud into historical buildings, into architectural elements, and eventually into geometric primitives. Okay, so I present some of the available data sets that I used in the experiments in this thesis. The first one is the Saint-Pierre Church in Strasbourg. So this is the same church as I showed you in the previous part. It's a 19th century church, and you see here that I put this icon to say that I use this point cloud for the first step, which is the classification of heritage complex into heritage buildings, and also for the detection and classification of pillars. The second data set is the Haut-Königsbourg Castle in Orschwiller in France. This one is the 12th century castle, and this data set I used for the detection of the wooden beams. The third data set is the Valentino Castle in Turin, which was shared to me by the people from the Politecnico di Torino, and I used this one for the detection of pillars. Fourth one is the Paestum dataset shared by the guys from FBK. And this is also interesting because it presents a very different architectural style for the algorithm to test. So here, of course, I use it to perform the pillar detection. And the last dataset is on the Kasupuan Palace in Cirebon in Indonesia. Again, we use this to present a very, very different architectural style to test the algorithm with. And for the Kasupuan one, I also used it for the step one and the detection of pillars. So step one is from heritage complex to heritage buildings. And the main idea here is to take the point cloud of a heritage site, and then we use the help of an existing GIS layer, so shapefiles. And we use the shapefiles to help with the segmentation of the point cloud. And since in the GIS layer, we usually already have the semantic information, we can then automatically attribute the semantic information into the clusters of segmented point cloud. Quickly, this is how it works. So we have the original point cloud and the GIS layer. So with the GIS layer, we have the geometry and the attributes. And then the first step would be to extract the ground from the original point cloud, and we take only the non-ground point cloud. We use the geometry of the GIS to perform what I call a cookie cutter segmentation, because you perform a 2.5D segmentation on the point cloud. And then from here, we have the object point cloud and the non-object point cloud. For the object point cloud, we can then annotate the attribute to create, in the end, a annotated object point cloud. This is the result. So you see that with the algorithm in M-Heracles, we managed to quite nicely segment the different classes of the scene. So we have the vegetation, the trees, the buildings, the gates and walls, and so on. So I did a small comparison with Metashape. This is the version of Metashape that I used. And should be noted that Metashape used a sort of machine learning approach to do this classification. And here we see that with M-Heracles, in the precision recall and F1 score is more or less significantly better than a Metashape. So step two, from buildings to architectural elements. Of course, the background of this step is there are different types of architectural style, and we want to use a common but simple universal geometrical rules to perform segmentation. And I have to date two classes available in M-Heracles, pillars and beams. So we will start now with the pillars, and we start with the point cloud of the building, which we get from the previous step. So there's a continuity here, and what we do here is we perform some slicings in order to detect the separate between the body of the building and the attic of the building. We take the body and perform another slicing cross section of the building, And with region growing, we can then extract the clusters of, let's say, islands of candidate pillars. And this is with a refined cookie cutter segmentation. We perform, let's say, a cleaning of the point cloud. And then what I added here is that we calculate the circularity value of each of the cross section of the candidate pillars. And in essence, if the circularity is near 1, then we can classify them as columns. So here, columns is defined in this particular sense as pillars having a circular, more or less circular cross section. And otherwise, they are classified as non-columns. These are the results from the 5 data sets that I tested MRACLIS with. This is the result for the segmentation, which is quite nice. So in 4 out of 5 cases, it managed to detect all of the pillars that it should be. So 20 out of 20 ground truth here, except for the Valentino. And this is easily explained by the fact that in this case, there are actually only 6 freestanding pillars, and the others are semi-pillars attached to the building walls. So here we have some error in the results of MRACLIS. For the classification part, again, for 4 out of 5 data sets, it worked very nicely. It managed to detect correctly the columns and non-columns. Even here in the case of Saint-Pierre, where they have double pillars, it managed to detect each individual pillars, except again for Valentino for obvious reasons. And this is on just the metrics here. We see that it works better for the class of 1. And again, for Valentino, we have a lower precision value. So for the second element, which is actually still in development, more or less. So what I did is that we take the original point cloud, and then I perform a normals-based region growth in order to extract the faces of the beam. And with the facet detection using hue transform, extract the individual facets for each individual beam. And then we introduce 2 geometric constraints. The first one is the graph adjacency. This means that if a facet is located next to another facet, then it will be linked by a graph. The second one is the parallelism check. So here we take the vectors, the main vectors of each facet. And the hypothesis here is that each constituent facet of a beam should theoretically be parallel on its longest axis. This means that the dot product of the vector should be near to 1. So with these 2 geometric constraints, I was able to extract individual beams from the, let's say, the wooden framework of the original point cloud. And if we perform a ransack, of course, we can then generate a geometric primitive, in this case, cuboids. Okay, so some conclusions and final remarks. For the first part, one thing that we notice here is that nowadays point cloud generation is a very straightforward process. Everyone can do it, but nevertheless, more advanced understanding is important in order to guarantee the quality of the product. And this is more important if we talk about posterity, if we want to use this product as a long-term documentation for the heritage object. And again, as in a lot of cases, automation is expected even in this case, because most of the traditional workflow requires a lot of time and resources. For the second part, we see that the segmentation and classification of point cloud gives a tangible sense, gives a semantic nature to the otherwise geometric point cloud. Progressive segmentation is useful and is a logical consequence of the multiscalar point cloud acquisition. And again, here we see that actually other approaches exist, like the machine and deep learning, with varying qualities and shortcomings, which is why we come into the further work here. that here I would like to emphasize that the philosophy of thesis is not to confront the different approaches to point cloud processing, but rather to complement them each other. So what we try to do for the next step of the research, which we are writing into a paper here, is to use mHeracles, the results from mHeracles, in order to help with the generation of training data for deep learning methods. So that is all from me, and I thank you for your attention, and I would be very happy to take questions and comments from you.
So thank you so much, Arnadi, for this really amazing talk and presentation. And honestly, I've learned some great stuff today. Now let's go to EFSTATHIOS and Margarita, who will be moderating the Q&As.
Thank you again, Ari. So first, I would like to ask if your supervisor who is attending would like to make any comment. Or else I have some questions of my own. But first, Margarita maybe can read the questions that we already have in the chat.
Thank you, Arnadi. I don't know if we have any comments. I guess not. So there is a question concerning slide 14, where you have the research about the indoor images and the comparison that you make on common type point between indoor and outdoor images. There is a question about that, if that's what exactly you're doing through the stained glass window. So I guess you should answer first that, if we got it right. And then we have a second question on that. If this is what you did, they are concerned if it's possible to select exactly the same point from indoor and outdoor windows.
Yes, to answer that question, it is true that we use the assumption that the type points are not exactly the same point, but we take the assumption that they are the same points by taking into account the the thickness of the window pane, which is about 2 or 3 centimeters.
Okay. So I guess you answered the last part about the error and the accuracy of that. I have a question on my own. If Stathis, you don't mind, I go first.
Sure, yes.
Okay, you talked a lot about Metashape, and I guess it's the most popular software, and pretty much everyone has heard about it or even used it. I was wondering if you tried to use also other software, and especially open source, since DBAT is also open source, and if you did, what results did you get?
Do you mean for the processing or for the quality control?
For the quality control.
Yes, actually, for the quality control, I also tested Micmac to recreate the project and see what how it works. The result is more or less in line with the results of DBAT, but of course, if you want to go into details, we wrote a paper about this, and I can share it with you if you are interested in it.
Okay, okay, thank you. We will check that. So Stathis, you can go on with your questions.
Okay, thank you, Margarita. So my first question was if you can clarify a bit, Ari, on how the GIS contributes to the classification and at what level of the process.
Okay. Yes, this is a very, very good question. I admit that I glossed a little over it with the presentation, but in essence, we know that in GIS you have in classical GIS, you have a two-dimensional vectors. So what I did is that I took the geometry of these GIS and I used them as a, I call it a cookie cutter, because what you do is that you slice the point cloud with an infinite altitude. So you use the geometry of the GIS file in order to segment this point cloud in a 2.5D dimension. And then, of course, afterwards, there are other algorithms that work in order to clean this point cloud. And then because that's for the geometry, but then because in GIS you also have the semantics, the attributes, you can then, let's say, annotate these attributes directly into the point cloud cluster that you just segmented using the geometry.
Okay, thank you. And the next question is for us that probably don't know about it. What is damping techniques about improving the bundle adjustment?
So damping techniques is, I think some people also call it optimization problem. So in essence, it's, you know, with bundle adjustment, you work with iterative process. And in these iterations, you also need a sort of approximate value. But sometimes your approximate value can be far away from the real value. So the damping method can help us to make this computation faster. In essence, is that, of course, mathematically it's much more complicated, but it's more or less like that.
No, okay, I think I get it now better. Thank you. And my last question is because, okay, that's maybe not on the topic, it's more of my interest, but I saw on one of your introductory slides a picture with a faro freestyle. Did you use it at all for your research, and with what results regarding noise?
First of all, I didn't the freestyle point cloud. I didn't use the directly in my thesis, but I did play around with it a little bit. And and secondly, we have a very early version of freestyle. And I have to say that the early results was not very good. It's quite noisy, but I was told that lately they have a later version that is better. But of course, I don't know because I didn't test that. But the one that I tested was quite noisy, and it was quite difficult to work inside the church because of the lack of lighting. When it gets a little bit dark, it's very difficult to get the automatic tie point matching between the different poses.
Okay, I can confirm that even the later version generates the same amount of noise, but anyway, even though it's supposed to be near infrared structure light, so with lighting conditions, it shouldn't have as many problems, but anyway. Okay, so that's
okay. I guess you have one more question. What is the impact of a lower precision point cloud on the classification?
So precision. So if we talk about precision, then this means, like, for example, how it was registered and so on. Of course, for the classification part, one of the main issues is if if you work with laser scanning, for example, you usually work from several stations, several points. And if the precision of your registration is not good enough, then you will have, I like to call it the ghost effect of like 2 layers of the same object. And of course, this can hinder it can make it more difficult for my algorithm to say that this is a pillar or something. So again, yes, if you work with laser scanning, please do it in a precise way, if possible.
So thank you so much, Arnadi, for your great presentation and topic, and we wish you all the luck in your defense, hopefully in the coming July, right?
Thank you. Yes, should be.
And of course, I thank the moderators and the participants for your wonderful questions. I would like to inform you that our next PhD talk will be on June the 2nd with Leah Ferrari, where she will be discussing her thesis, Securing Damaged Churches and Bell Towers, so don't miss that. At the end, please stay connected to our Facebook group and Instagram page, where I am posting right now their link in the chat box for you to check. And please don't forget to subscribe to our new YouTube channel, CIPA IP, where we will be posting the recording of today's talk in addition to our previous and coming webinars. Additionally, we encourage you to visit the CIPA webpage and ICOMOS webpage for more information about this organization. So see you soon, and thank you so much.
Thank you.